Everything that we've done up to this point, folks, for the most part, was just techniques of solving a differential equation of order 1. Okay? Some cases they were nonlinear, most cases they were linear, right? But they were all just pretty much order of 1. We had an example that I gave you where we had a differential equation of order 2 and we reduced it to a differential equation of order 1 with a simple substitution. For the most part, that's the order 1 analysis. Let's now look at some applications of these type of differential equations. First application is an application that you used, that you should have been introduced to back in Calc 1. And that's orthogonal trajectories. How many of you folks remember or ever heard of an orthogonal trajectory? Do you remember it back in your Calc 1 class? Did any of you do an orthogonal trajectory? What is an orthogonal trajectory? Yeah. It's when you have two curves, or in some cases, family of curves, right? You have two curves that cross, and they cross orthogonally, meaning perpendicular, meaning that the tangent lines at the point of intersection are perpendicular. Okay? So if I had a curve, for example, like this, and another curve like this is f of x, and this is g of x, then right at the point, well, that's not a very good drawing. Right at the point of intersection, this is g of x, then at the point of intersection, right there, there's one tangent, there's another tangent, boom, the two tangents are perpendicular. Then you can say that those two, f of x and g of x, are orthogonal trajectories of each other. Okay? Sometimes you have family of curves. You might have something like this. You might have a family of curves of radial lines, like so. And another family of curves of concentric circles. Anybody know what the equation of these concentric, or these radial lines are? What's the family of curves? Good. Yeah. Y equals cx, which c is any number. Y, this is really the slope. These are all lines, y equaling mx, going through the center, right? No plus b, they have no y-intercept. And c is a constant, so this could be any slope. So you've taken all the possible slopes. This will include all, there's a singular solution in here. What's the singular solution? No, that's picking c equaling 0. What kind of line is that? Vertical. What's the slope of a vertical line? Doesn't exist, right? So there's no value of c that you can put in this to get x equaling 0. Right? So there's a singular solution in this family. Oh,
Would that there are multiple singular ones then, right? Because it would be any point where the circle is.
no, this is for the lines.
Oh, okay.
Right? Now, what's the equation of these concentric circles? Let's use a different, let's use k squared. It may not be the same constant as this, right? But that's all, it's just the radius squared. X squared plus y squared equaling r squared is the equation of a circle centered at the origin. And r could be, or this k could be any radius. So you have a bunch of concentric circles. Well, these two families can be orthogonal trajectories of each other. Meaning that wherever the lines cross the circle, they're perpendicular. Everywhere. Does everybody understand that? So then, therefore, you would say that those two family of curves are orthogonal trajectories of each other. Well, let's think. How would we go about mathematically testing orthogonal trajectories? Well, if you recall back from Calc 1, if you had this in Calc 1, you found that, well, if they're perpendicular at the point of intersection, then the slope of the tangent line to this curve should be perpendicular to the slope of the tangent line, the slope of the tangent line of this curve should be the negative reciprocal of the slope of the tangent line to this curve, right? Perpendicular lines have negative reciprocal slopes. Or, better yet, if you took the two slopes, if I took the slope of this tangent line, took the slope of this tangent line, and multiplied them together, what are you going to get? -1. So that's really the test for orthogonal trajectories. I take the slopes of both tangent lines. How do I find the slope of the tangent line to a curve? Take a simple derivative, right? In this case, I would have to take a derivative. I'd have to use implicit differentiation. I would say, okay, now remember, which derivative is the slope of a tangent line? dy dx, not dx dy, not dr d theta, not any other derivative, just the one derivative, dy dx. The derivative of y with respect to x, right? This is the change in y's over the change in x's. Isn't that how we define slope? The rise over the run, difference of the y's over the difference of the x's. This is the only derivative that depicts slope. All right? And this is obviously, we're doing this problem in a Cartesian coordinate system. That means I have to find the derivative of y with respect to x for both of these curves. And then if I took the two slopes and multiplied them together, I should get -1 every place where they intersect. Correct? So let's trust it on this. Let's see if this in fact is the case, that they're orthogonal trajectories of each other. Let's find the derivative of y with respect to x. Here I would have to use implicit differentiation. This is 2x plus 2y dy dx equaling 0, because k is a constant. So this would be dy dx would equal, moving the 2x on the other side, get -2x over 2y, which is a -x over y. So there's a formula for the slope of the tangent line to the circles for any x and y value. Let's take the slope of the tangent line here. dy dx equals, what's the derivative of this? C, huh? Which actually kind of makes sense because there's your slope, y equals mx. All right, so what did I do? I take these two and multiply them together. If I take c times a -x over y, let's see if that gives me a -1. This is the -cx over y. Is that -1? Well, now remember, this is at the points of intersection, right? At the point of intersection, what does -cx equal to? Well, isn't cx equal just to y? So I can do a substitution, and I get -1. So in fact, these two family of curves do intersect at right angles. They are orthogonal trajectories of each other. You should have got this in Calc 1. Everything here is Calc 1. I have not shown you anything dealing with Calc 2. Let's take another example. Let's do something you might not have done in Calc 1. Let's say, I want you to find, I give you a function, y equaling c over x, and I want you to find a function, or actually better, find the orthogonal trajectories of y equaling c over x. I want to find the function, find some function that is the orthogonal trajectory of y equaling c over x. And that function might just be a family of curves. Okay? How would I go about working this? In other words, I'm not taking two known functions and trying to see if they are orthogonal trajectories of each other. I'm giving you one function, known, and I want you to find the other function that would make this set an orthogonal trajectory set. Okay? Now the way you would actually go about doing this is that you would actually develop a differential equation from this, because again, isn't the slopes have to be -1, right? The product of the slopes have to be -1, and the slopes are derivatives. So if I created a differential equation for this, where this is the solution, that first order differential equation really will depict the slope of the tangent line. Watch. Let's take the derivative of this. What's the derivative of this? Right? Now what I'm going to do is I'm going to go one step further. This is the slope of the tangent line to this curve, but it's in terms of c. I'm going to eliminate the constant and actually come up with the differential equation that this is the solution to. How do I eliminate the c? Well, go over here. I see that c is equal to x times y, isn't it? So I am going to substitute that into here, and I'll get a negative xy over x squared. So dy dx equals a negative y over x. This still, folks, this is really the differential equation. If I solve this, and I can easily solve this by separation, right? That if I solve this by the technique of separation of variables, I will get that as a solution, a general solution. This also represents, dy dx, also represents the slope of the tangent line to this curve for any x and y. Do you understand? If I'm looking for a function that is an orthogonal trajectory of this function, what do you know its derivative must be? If the derivative of this function, if the slope of the tangent line of this function is a negative y over x, what must the slope of the tangent line or the derivative of this function be? X over y, right? The negative reciprocal of this. So I know, just by looking at the differential equation, which represents the slope of the tangent lines, I know that this function, I'll do it in a different color, I know that f of x must have a differential equation that looks like this. Yes or no? Yes or no? This is the slope of the tangent line for curve 1 for y equaling c over x. This is now the negative reciprocal of that, meaning that whatever solution comes out of this differential equation, those solutions must be orthogonal trajectories of these solutions. Yes or no? No? How about a yes? Well, you may say yes, but your eyes say no. That says no. That means you don't understand. Do you understand it or not? No, yes? One more time?
Yes.
You concede way too easy. All right, let me do it one more time. Y equaling c of x. I'm trying to find some function that is an orthogonal trajectory, meaning that the slope of the tangent line of this function is the negative reciprocal of the slope of the tangent line to this function. Right? Because they're perpendicular tangent lines. Yes or no?
Yes.
Everybody.
Yes.
All right, now I know you're awake. Come on, we're almost done. Yeah, see, yeah, just for the heck of it. All right, so this is the idea, this is the concept. If I take this function, find its slope of the tangent line, which is its derivative, right there, right? And what I did is I eliminated a constant to get a more general form, negative y over x, where y is this and x is x. In other words, if you plug y back into here, you'll get that expression back. This now represents, look, derivative of y with respect to x. This represents the slope of the tangent line to this curve. Well, I know if I'm trying to find the orthogonal trajectories to this family of curves, the slope of the tangent line of this function must be negative reciprocals of the slope of the tangent line to this function. The slopes must be negative reciprocals. Well, if this is the slope of this function, which is a negative y over x, what's a negative reciprocal? You flip the number and you take the negative of it, right? 1/2. What's the negative reciprocal of 1/2? -2. If you take 5, what's the negative reciprocal of 5? -1/5, right? So I'm looking for the slope of a tangent line to this curve that's a negative reciprocal of this. So the slope of the tangent line to our second curve, the f of x, must be the negative reciprocal. So take the negative reciprocal of this. Flip it, take the sign, you get x over y. Do you understand?
Yes.
Now I solve this differential equation, because it is in fact a differential equation. I solve this differential equation, separation of variable, and the solution will be then orthogonal to the original function. What is this? Y squared over 2 equaling x, well wait a minute, what did I do here? X squared over 2 plus a constant. So this is going to be multiplied straight by 2, you'll get y squared minus x squared equaling a constant. Right? What kind of curves are those? Conic sections, folks. Calc 2. What kind of curves are those? You need this. What is it? You asking me or telling me? What's he doing? Is he asking me or telling me? Mine was a question. His should have been an answer. What is it? You're right. That's a hyperbola, right? How do those hyperbolas look? Where's the center of that hyperbola? Good. Origin. These hyperbolas, depending on the value of c, will be hyperbolas like this. Could they be like that? How about like this? Could they be like this? Actually, if c is negative, you'll have hyperbolas that open along the x-axis. C's are positive, you'll have them open along the y-axis. But you're going to have a series of hyperbolas that look like this. Do you remember your conic sections, folks? Hyperbolas? No. That one are these. Now, that's this family. What is y equaling c over x? That's the reciprocal function, right? Or xy equaling c? That's a cross term of a conic section. Calc 2, cross terms. What do cross terms do in the conic section? It's your day to get picked on because it's almost time to quit. Cross terms. What does it do to our conic section? He beat you to it. Like always, he beats you to it. I know, I'll point to you next.
Thanks.
Rotates the conic section. I'm testing because they had me for Calc 2, and if they would have failed, I would have failed. They would not have gotten that question, they would have both failed this course. If he would not have answered the right question, you would have failed this course. Okay? It rotates your conic section. Does anybody know what kind of a conic section this is? You should know the reciprocal function looks like, yay, doesn't it? Well, that's actually a family of hyperbolas that are rotated how many degrees? 45 degrees. So if I drew the family of curves y equaling cx, it looks like this. Depending on the values of c, I'd have this family. And anywhere the blue lines cross the red lines, you have a voting nightmare. I mean, where you have blue lines and red lines crossing, they're orthogonal. They're perpendicular. Right? Right? Right there. Perpendicular. Looks it. You understand? Does everybody understand this? Next time, which is what? Tomorrow. We're going to do orthogonal trajectory. This is all in Cartesian coordinates, right? Where the slope of the tangent line is the derivative of y with respect to x. To Tomorrow we're going to be dealing with orthogonal trajectories in polar. Now, let me ask you a question before you all run out of here screaming. Because I'm now picking on people. Don't worry, folks. How many of you folks hate those classes where teachers would pick on you? Just out of the clear blue sky, blah, 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 blah. And you're going, whoa, wait, what? What? Me? Right? How many of you folks have ever had a class where teachers did that? How many of you folks appreciated that? See, he doesn't mind it. He surely doesn't mind it. So that's why I pick on those two. But the rest of you are safe. That's just because, like I said, they're relatives. See the resemblance? Relatives. Now, before you run away, polar coordinates. You remember polar coordinates? Do you remember functions in polar coordinates? R is some function of theta. Right? I want to find the slope of the tangent line to this curve. Will that do it? Y equals f of x. Derivative of y with respect to x. Does that show me the slope of the tangent line to this curve? This is the derivative of r with respect to theta. Does this show me the slope of the tangent line to this curve? No. So if I wanted to find orthogonal trajectories and deal with tangent lines being perpendicular, tangent lines, unfortunately, is really a rectangular thing. It deals with the rise over the run. It's very rectangular, right? The change in y is over the change of x. When you're dealing in polar, where you plot points by swinging an angle and shooting out a radius, there's no rise over run concept in that coordinate system. So if we wanted to find orthogonal trajectories in polar, the derivation is a lot more convoluted, but we're going to come up with a result very similar to what we would get in the rectangular coordinate system. But dr d theta, what does that mean? This means the change in the rise over the change in the run. This is actually the slope of the tangent line. The rate of change of y when you move x, when x moves. What does this mean? That's right. This means the rate of change of your radius, and remember how you plot points. You swing up and then you shoot out, don't you? For polar coordinates. This really represents the rate of change of your r, your radius, as you're swinging your angle. So it's really like a windshield wiper moving. And think of a windshield wiper moving, but the length of the windshield wiper is expanding or contracting as it's sweeping. This measures how fast the windshield wiper is growing or compressing as you're sweeping. So it measures how fast your arm is extending out as you sweep, or how fast the arm is pulling in as you sweep.
It's kind of like traversing an ellipse or something.
Well, it depends on how it pulls out and pulls in. All of your polar coordinate curves, all of your polar curves, is essentially drawn by, think of it as a pen at the end of a windshield wiper. And my windshield wiper, instead of going like this, it's going all the way around. And my pen at the end of that windshield wiper, a variable, flexible windshield wiper, is moving in and out. And as I circle, that windshield wiper is moving in and out, drawing all of the polar curves that you've had in Calc 2. And this measures the rate in which, how fast the arm is extending out as you're sweeping, and how fast it's pulling back in. Does that have anything to do with rise over the run? Slopes of tangent lines? No. Does anybody, and we'll do it tomorrow, does anybody know what you have to do, and this should have been a Calc 2 deal, folks, what you have to do if you wanted to find, for example, the tangent line to some polar curve? How would you find the slope of a tangent line when you're given a curve r equaling r theta? You can't just take the derivative and say, I'll do it that way. That has nothing to do with slopes of tangent lines. Speak up. Oh, so see, I should pick on you then. Wait a minute, give me a chance. You. Hey, see, it wasn't that bad, was it? Parametric equations are exactly right. What you have to do, folks, you have to take a polar curve, setting you up for tomorrow, Calc 2 review. You have to take this polar curve and you have to write it in parametric form. X equaling r theta cosine theta, y equaling r theta sine theta. Do you recall that? This gives you the polar curve written in terms of x and y, really kind of a hybrid between the two coordinate systems, because I'm still dealing in polar here, but rectangular on that side. That's the beauty of parameterizing polar curves this way. And then how do you find the derivative of y with respect to x? Well, it's just taking the derivative of this this group of parametric equations. Isn't the derivative of y with respect to x the derivative of y with respect to theta over the derivative of x with respect to theta? And I can take the derivative of y with respect to theta, because these are all functions of theta, and I can take the derivative of x with respect to theta, divide the two out. I'll have a bunch of polar stuff on this side, but it would represent the slope of the tangent line. Polar orthogonal trajectories. In polar coordinates, we're not that fortunate to have a way to determine if two curves or two polar curves are orthogonal trajectories of each other. And the reason why is because the slope in polar is not an easy thing to find. Slope of a tangent line in polar. Slopes of tangent lines are really a rectangular coordinate phenomenon. It's defined in a rectangular coordinate system. Slope, rise over run. In polar, and I think I talked about this yesterday. Now I remember where I am. I talked about this yesterday. In polar, when you plot points, the way polar coordinates works in sketching out curves, it's a radial arm being swung like a windshield, right? Swinging out an angle, shooting out, boom, locating a point. Rise over run really has no place in that type of a coordinate system. So how do we find whether two polar curves are orthogonal trajectories of each other? In other words, are perpendicular, the tangent lines are perpendicular. Well, even to find tangent lines in polar is a difficult thing. But do you recall from Calc 2 though, if I had r equaling r of theta, let's say if I have my first curve, r1, equaling r of theta, and I have a second polar curve. Okay, I have two polar curves. I could find slopes of tangent lines to these curves by writing both of these polar curves in terms of a parameter, writing it in a parametric set, where and I think I talked about this yesterday, where you take advantage of both coordinate systems. And what is the transformation that you would use to transform these into a rectangular parameter set?
X equals r cosine theta. Y equals r sine theta.
Because if you notice, between there's theta, this is x, this is y, this is r. This point can either be called xy, or it could be called r theta. And to relate x, right, the r theta is the polar version of this point, xy is the Cartesian coordinate version of this point. And in order to write x in terms of r and theta, and y in terms of r and theta, we see that x is simply r cosine theta, and y is simply r sine theta from the little trig. So this is a great way of taking a polar curve and writing it in a parametric form where we can take advantage of the Cartesian coordinate system. So if this polar curve was written in terms of this, you would have it as x equaling r of theta, cosine theta, and y equaling r theta, sine theta. This is r1, so this is x1, y1. And this other polar curve can be written like this. x2 equaling r2 theta, cosine theta, and y2 equaling r2 theta, sine theta, correct? And then in Calc 2 did you find slopes of tangent lines to polar curves? Well, the slope of a tangent line, if you recall from yesterday, I stated that a slope of a tangent line, there's only one derivative that's going to give you the slope of a tangent line, right? And that's a rectangular coordinate derivative, the derivative of y with respect to x. That's the change in y over the change in x. That's your slope form. Well, how do you find the derivative of y with respect to x when you're written in terms of a parametric equation? The derivative of y with respect to theta, because notice this x is now a function of theta and theta only. This is a function of theta only. Isn't the derivative of y with respect to x equal to the derivative of y with respect to theta over the derivative of x with respect to theta? Right, back in Calc 2. So I would say, oh, okay, let's take the derivative of y with respect to theta. And notice both of these are functions of theta, so you've got to use the product rule. So you have to go, oh, that's the first times the derivative of the second plus the second times the derivative of the first. All over the derivative of x with respect to theta, and that's going to be r1 minus sine of theta plus dr1 d theta cosine theta. And that would then represent your derivative of y with respect to x, still keeping your function written in terms of polar functions. And notice, this represents the slope of the tangent line to this curve. And it's not equal to dr d theta, is it? It's equal to all this mess. Does everybody see that? And then I can say, well, you know what? I can do the exact same thing for this other curve. Find dy dx for this other curve, this other parametric set. And then say that this derivative must be the negative reciprocal, or this quantity must be the negative reciprocal of this quantity. In other words, if I use this one and I said dy dx for this particular set, which would be what? r2 cosine theta plus dr2 d theta sine of theta over negative r2 sine theta plus dr2 d theta cosine theta. Does everybody follow? And then you could say dy, I'll put a 2 here and I'll put a 1 here, so you can designate the difference, distinguish the difference. You can say dy dx 1 times dy dx 2 gives you what? So I could then say, all right, let's take that first quantity, r1 cosine theta plus r1 prime sine theta over r1 prime cosine theta minus r1 sine theta, times it by r2 cosine theta plus r2 prime sine theta over r2 prime cosine theta minus r2 sine theta, and that should equal -1. Right? Big mess. Try to simplify it. You're not going to get very far. Matter of fact, to try to come up with some easy, convenient way of checking whether two polar curves are orthogonal trajectories of each other, this is not the way. So we're going to have to look. Does everybody understand that this would work? If you took the first polar curve and you did this to it, took the second polar curve, did this to it, multiplied them together, and if you got a -1, yep, they're orthogonal trajectories of each other. Yes?
The dy dx2, is that the negative inverse of dy dx1?
You can say, actually, the negative reciprocal, yes.
Should it be flipped? Should the r2 sine theta be on top?
No, because I'm multiplying the two slopes together. This is just m1, m2 equaling a -1. If I wanted to set this equal to each other, I could say this one equals -1 over this one, if I algebraically moved it over. But you just take the two slopes and you multiply them together. And if that gives you a -1, then you have orthogonal trajectories. This is trying to do polar coordinates, trying to do curves in polar coordinates with a rectangular coordinate mentality. Got a problem, because this is not an easy thing to do. It's a lot of work, a lot of derivatives playing around. I'm going to show you another way to find whether two polar curves are orthogonal, or orthogonal trajectories of each other. Now the derivation is going to be a little lengthy, a little bit of algebra involved, but you'll see that the result will be a very, very simple result. As simple as m1 times m2 equaling a -1, or the two derivatives equaling -1 in Cartesian coordinate system. This is a very easy thing to check in a Cartesian coordinate system, right? Take the derivative of one function, take the derivative of the other, multiply them together, you got -1. Here, it's not as easy as taking the derivative of r with respect to theta, taking the derivative of the other r with respect to theta, and multiplying them together and getting something. It's not that easy yet. Okay, does everybody understand? This is a correct way of looking at it, but we're looking at a polar problem through Cartesian eyes, not a clean way of doing it. So let's wipe this out. Although if you ever get stuck, you can do it that way. And let's look at how I'm going to treat orthogonal trajectories in polar. Let's say I have a polar curve, and we'll call this R1 of theta. And I have another polar curve. Let's do this. There's my R2 of theta. Okay? And at the point of intersection, right there, I'm going to draw the radial arm. That's R. And I'm going to extend that radial arm out. And this is actually called the radial line. Okay, or the radial axis. So the radial line. Now I'm going to draw tangent lines. Where's my green? There they are. I'm going to draw tangent lines to these curves. Here is the tangent line. And the other curve is right here. There's the tangent line right there. So this is T1 and this is T2. Now we know that in order for these two curves to be orthogonal trajectories of each other, those two tangent lines have to be, boom, right angles. Right? Now the way we're going to measure, the way we're going to treat this problem is that we're going to introduce an angle measured from the radial line going counterclockwise. We will measure the angle to the tangents. So this angle right here, we're going to call this psi. We'll call this psi 1, Greek letter psi. And this angle from here to here, psi 2. All right, does everybody understand that? Now let's look at these two angles. If we're measuring from the radial line to the tangent, going in a counterclockwise fashion, I see that psi 2 minus psi 1 must equal what?
90 degrees.
You all see that? This angle minus this angle has to give me that angle, which is 90 degrees. Pi halves. Because they're orthogonal trajectories of each other. So that means psi 2 equals pi halves plus psi 1. Let's play around with the trig here. Let's take the tangent of both sides. I'm taking the tangent of psi 2, which equals the tangent of psi 1 plus pi halves. I can use a trig identity. What's the tangent of psi 1 plus pi halves? Look at your front. Is there an identity? Anybody know this identity? Tangent of a plus b? What is it? You're going to make me try to memorize it? I don't remember it. You're supposed to remember it. But I think it's tangent of psi 1 minus the tangent of pi halves over 1 plus the tangent of pi halves times... Oh no, I'll take that back. I know an easier way. Isn't that just equal to the cotangent of psi 1? Yeah. Isn't cotangent a cofunction of the tangent? Right? Aren't these... Actually, let me see. Hold on a second. Actually, that's a... It's a minus cotangent. All right, let me just do this. Let's start where we left off. Last time, we were doing applications of linear differential equations. And the first application was one of radioactive decay, right? We modeled a problem of radioactive decay and then solved the differential equation and got whatever we were looking for. Here's a second example of an application of a linear differential equation. This is an example or an application of Newton's law of cooling. If you had an object that was heated up and you set it let's say, for example, on the table, and you allow this object to cool, you can model that physical phenomena by this expression, stating Newton found that, and this is a simplified model, this doesn't always happen for all temperatures, but nevertheless, Newton found that the rate in which an object cools, which is going to be the rate of change of temperature with respect to time, is proportional to the change in temperature, the temperature difference between your object and the ambient, the object and its surroundings. Therefore, from this relationship, a differential equation can be had, that the rate of change of temperature with respect to time is equal to K, K is just the proportionality constant, times the temperature difference, which is the temperature of the object, T, minus the temperature of the ambient, temperature of your surroundings. All right? Solving this differential equations will get you then an equation of the temperature cooling, a temperature distribution of that object that's cooling. Let's take an example and work it. Let's say I have a pizza coming out of the oven. All right? You're at my house, homemade pizza. The stuff that never cools off. Pizza out of the oven comes out of the oven at 400 degrees Fahrenheit. 5 minutes later, measured the temperature of the pizza and was at 300 degrees. So obviously the pizza's cooling off, right? It's on the counter cooling off. I want to know how long it would take for the pizza to cool to room temperature, which is at 70 degrees Fahrenheit. So this pizza starts at 400 degrees, 5 minutes later it's at 300, and obviously over time it's going to eventually become the temperature of the room, 70 degrees. Okay? So T of 0, T at time 0 is 400, T at time 5 minutes is 300, and I want to find the time, the temperature, I want to find the time it takes to have the temperature at 70 degrees. Okay? Let's set this up, differential equation. We know that the rate of change of temperature with respect to time is equal to some constant times T minus T ambient, and in this case, what's our ambient temperature? 70. So there's our differential equation for this particular problem. We need to solve it. Well, this is simply a separable differential equation of order 1. It's a linear differential equation. Let's solve this. We can write this as dt over t minus 70 equaling kt, kdt. Integrating both sides, I get the ln of t minus 70 equaling kt plus c, or t minus 70 equaling c e to the kt. Right? Exponentiate both sides. Or you get the temperature equals 70 plus c e to the kt. Now we need to find the constant of integration, c, and our proportionality constant, this k, which is a measurement of the thermal conductivity of the material. Notice, if you have a material, or actually, if the material that the object is made out of is a good insulator, it may not cool off as fast as something that's a good conductor of heat, correct? And that proportionality constant will indicate what type of material you have. But nevertheless, let's find our C and our K. We can use our conditions. Initial condition, at time equaling 0, T is 400. So in using that, I'll have 400 equaling 70 plus C e to the 0, which is just C equaling 330. Oops. So this temperature now, temperature distribution is T equaling 70 plus 330 e to the kt. Still have one more constant to find before I actually have the temperature distribution of my pizza. And I can find that just by this other test point, this other initial point. At time equaling 5, my pizza is 300 degrees. So at temperature is 300 at time equaling 5. So we have 300 equaling 70 plus 330 e to the 5k. Solve back for k. You should all be obviously able to solve for k. And if you solve for k, you get k equaling, anybody solve that before I do?
-0.0722.
Negative 0.0722. So therefore your temperature distribution in time is equal to 70 plus 330 e to the negative 0.0722 t. This is a model of the temperature distribution of the, or the temperature cooling of the pizza over time. At time equaling 0, you'll have this be 1, 330 plus 70 gives you 400 degrees. At time equaling 5, you plug a 5 in there and you will get 300 degrees. I want to know, how long will it take for the pizza to cool to room temperature? Well, notice, if I plug in, for it to be cooling to room temperature, what does this quantity need to be?
0.
Needs to be 0, right? So, how do I get this quantity to be 0? What does t then need to go to?
Infinity.
T needs to go to infinity, right? So if I took the limit of this temperature distribution as time went to infinity, let's see what temperature distribution, or what temperature this pizza would be at if I just let it sit on my table forever. This would be 70 plus 330 e to the minus 0.0722 times infinity. Obviously that's 1 over e to the infinity, which goes to 0. Hey, this thing approaches 70 degrees. Does this mean that I have to allow the pizza to sit on my table forever? It will essentially never reach room temperature? Well, we know that's not the case, right? Our pizza, you ever tried 2-3 day old pizza? Matter of fact, sometimes the pizza even gets colder than your ambient, right? It just starts to gel and freeze. At least if you buy pizza where I buy it from. So we know this is not the case. So what's wrong with our model? Well, actually what's wrong with our model is this. This is a simplified version of an object cooling. This proportion isn't always the case. And it is good for large temperature distribution or large temperature differences. For example, when this pizza first started cooling, 400 to 300 to 200 and so forth, if there's a big spread between your ambient temperature, your room temperature, and your pizza or your object's temperature, then this will be a pretty good model. It's an exponential decrease, exponential cooling. But what happens as these two approach each other, as the temperature of the pizza, for example, in this case, approaches the temperature of the ambient, you start getting nonlinear effects occurring. And to model that, you would have to actually modify this expression and actually get a situation where you have a higher order nonlinear differential equation, because you have to take into other thermal accounts, thermal properties. But for a simplified model, boom, this works. Everybody understand how we solved it? Okay? Let's look at our next example. Next example of a linear differential equation, modeling something that gives me a linear differential equation and then solving it. And the second case is that mixture of two salt solutions. Let's say I have a tank. And I'll draw a picture over here. There's my tank. And in this tank, I initially have 50 pounds of salt, and it's dissolved. So here we go. Here we have 50 pounds of salt dissolved in a tank with 300 gallons of water. So we have 300 gallons in this tank initially. A brine solution is pumped into the tank at a rate of 3 gallons per minute. So brine, salt water, is being pumped in at a rate of 3 gallons per minute. And we state that the concentration of that brine solution is 2 pounds of salt per gallon. So initially here we have 2 pounds of salt per gallon. Okay? So there's the concentration, 2 pounds of salt per gallon being, 2 pounds of salt per gallon, and then 3 gallons per minute being pumped into this tank. Obviously, it's going to change the concentration of salt in the tank, isn't it? And then we have the mixture, well stirred, so that you don't have any type of concentration distributions running through this. It's all homogeneously mixed. The well stirred solution is then pumped out of the tank at a rate of 2 gallons per minute. So now it comes out of the tank in this process at 2 gallons per minute. So you have 3 gallons per minute going in, 2 gallons per minute going out. Determine the amount of salt in the tank at any time t. And then I want to know how much salt is in the tank after 50 minutes. Okay? So I want to know, I'll call this S of t equals the amount of salt in tank at time t, which I state right here. S of t is the amount of salt in the tank at any time t. Well, if you look at this problem, this is really just a related rate, something like you had back in Calc 1. But out of the related rate problem, you'll end up with a differential equation that you'll need to solve. A linear differential equation of order 1. Well, in this particular case, we can say that the rate in which the salt is changing in the tank is really just the difference between the rate in which the salt is entering minus the rate in which the salt is leaving. Right? The difference of the amount of salts that are going in and out will give you either an additional salt concentration here, or it'll increase the salt concentration or decrease the salt concentration. So the rate of change of the salt in the tank is simply equal to the rate of salt entering the tank minus the rate of salt leaving the tank. How fast it's coming in, how fast the salt is coming in, minus how fast the salt is leaving. Well, how do we write this? The rate of change of the salt in the tank water can simply be written as the rate of change of S, and this is S of t, with respect to time. And that equals the rate of change of S in, with respect to time, minus the rate of change, the time rate of change of S out. Does everybody follow so far? Now all we have to do is get expressions for these two. We'll have a differential equation of S in terms of t, and we can solve that differential equation getting a formula, getting a function of S written in terms of time. How do we go about doing that? Well, let's look. How do we actually find the rate of change of the salt coming in? Well, if you took the concentration of the salt coming in times the flow rate, think about this. What's the concentration of our salt coming in? Well, isn't it 2 pounds of salt per gallon? And if I times it by the flow rate and what's the amount of salt or amount of fluid that's coming in, brine? 3 gallons per minute. You'll actually have 6 pounds of salt per minute coming into the tank. And that's the rate of change of the salt coming in with respect to time. It's the rate of salt entering the tank. 6 pounds of salt per minute. Does everybody follow that? Now we have to do it for this salt leaving. So let me write this differential equation over here because I have obviously more room. All right, the rate of change of the salt in the tank with respect to time is equal to, in our first case, we got 6 pounds of salt per minute. And we're going to now minus the amount of salt, the rate of change of salt coming out of the tank. And that, again, is the concentration of that salt, which we weren't given, times the flow rate, which we were given. So this would be the concentration times the flow rate. And our flow rate is 2 gallons per minute. Now, the hardest part of this problem is really writing the concentration of the brine that's leaving. Well, how do you find a concentration? Well, notice the concentration just tells you the number of pounds of salt divided by the total volume, right? So in other words, the stuff that's coming out, the concentration of this stuff that's coming out is the same concentration that's in the tank because it's leaving the tank at that time t. Well, how much salt do we have in the tank at any time t? S of t. So this would be S of t divided by, now I have to think about what's the, at any time t, what's the amount of gallons? What's the volume? Well, we start off with 300 gallons. And then for every minute, what are we doing?
We're adding a gallon.
We're adding 1 gallon per minute to the tank, aren't we? We have 3 gallons going in, 2 gallons going out. So there's a net of 1 gallon per minute being added to this 300 gallons. So my total volume of the tank, the total volume of the salt solution at any given time t would be 300 plus, well, we have 1 gallon per minute, so we'll have 1 gallon per minute times t minutes. Or we can write this as ds dt equaling 6 minus s over 300 plus 1 times t times 2. And there's our differential equation. Does everybody see that? So the total volume is 300 plus 1 times t. Gives me the total volume at any time t. This times 2 then gives me the rate of the salt leaving. So we have the rate of the salt entering minus the rate of the salt leaving has to give me the rate of change of salt in the tank. I have a differential equation here. How do I go about solving it? Well, notice this is actually a linear differential equation. I can write it like this. See how it's linear in S? This is this quantity right here is your P of T. And our integrating factor then, we're going to solve this using an integrating factor. V of T then would be E raised to the integral of P of T, which is 2 over 300 plus T dt. Does everybody follow? What is this? This is equal to E times 2 ln of 300 plus t, which is equal to just 300 plus t quantity squared, once you simplify. So there's my integrating factor. Well, how do I go about solving this? I'm going to erase this. Now I take this integrating factor, multiply it through, and what do I get? I get 300 plus t quantity squared ds dt plus 2 times this quantity, which one of these cancels with one of those, just giving me 300 plus t to the first, s, equaling 6 times 300 plus t quantity squared. I see this is now a total differential, isn't it? Where the first is this 300 plus t quantity squared, and my second is s. Notice if you wrote it as 300, the total derivative, total differential of 300 plus t quantity squared times s, you'd have first times the derivative of the second, there it is, first times the derivative of the second, plus the second times the derivative of the first. The derivative of this is 2 times this quantity of the first. Boom, there it is. That equals this, 6, 300 plus t quantity squared. And now I integrate both sides, just solving a linear differential equation of order 1. This becomes just 300 plus t quantity squared s equaling, integrating this, and what do we get? You'll get 6. If you use simple use substitution, you'll have just this, 300 plus t cubed over 3 plus some constant. So dividing this out, we'll have s of t now equaling, this is 2. You'll have 2 times 300 plus t, right? Because if you divide this on the other side, 2 of these will go, plus a constant divided by 300 plus t quantity squared. We have an integration constant we need to find. What can we use? Well, this is now a formula, or an equation that depicts the amount of salt in the tank at any given time t. Well, at time equaling 0, how much salt do I have in the tank? So I have a condition there. At time equaling 0, the amount of salt in the tank is 50 pounds. And that's going to allow me to solve for C. So I let 50 equal, plug T equaling 0, and I'll have 600 plus C over 300 squared. Solving for C, what do we get when we solve for C? I'll tell you in a minute. Negative 4.5, negative 4.95 times 10 to the 7th. Yep. Therefore, plugging that back in, minus 4.95 times 10 to the 7th. This now constitutes a mathematical model of the amount of salt in your tank at any given time, T. So if I wanted to know, I have erased the problem, but the problem asks you for how much salt would be in the tank. What was it, 50 minutes? How would you find that out? Yeah, just plug in 50 into your final form, and you'll get the amount of salt that's in the tank 50 minutes after you started pouring and draining the two brine solutions. Ravish? If I wanted to know how much salt would I have in the tank as time goes to infinity, well, if you let time go to infinity, this quantity does what? And all you have is this, and you let this go to infinity, what's your salt going to go to? Why is that? Because notice, folks, yeah, the concentration of this is more than what's in the tank. And you're putting in more than you're not. So this concentration in the tank is constantly on the rise. The amount of salt in the tank is constantly on the rise. Well, because of the physical constraints of the tank, yeah, how can you fit an infinite amount of salt, right? Pack it in really tight. So we're assuming my tank goes up and up and up and up and up. The tank is, my swimming pool in my backyard, which has no bottom. Everybody got it? Everybody understand? I don't have a swimming pool without a bottom. I call it a mud puddle. It's when it's monsoon season, I live real close to some wash that just keeps getting deeper every year. Nice place to play. Nice place to, drive up and down in it. Everybody got it? Yes? Okay. Let's try some examples of nonlinear differential equations. Applications in nonlinear cases. I'm going to give you two. What's the problem? What don't you like? What don't you like about me? What'd you say?
I love this class.
And he's saying that before taking an exam. All right, our first application. We're going to go back to this logistic equation. We talked a little bit about it last time, right? A logistic equation, which is a special case of the Bernoulli differential equation. This logistic equation is an equation that can depict or model population growth that's subject to some type of constraint, right? When you have which really models true life population growth. If you were modeling a population growth of some species or some group, it's not going to grow forever. There's going to be limiting food supplies, limited space, limited air, limited supplies that the population needs to expand. So you're going to have deaths, right? So in taking into account deaths, your population can possibly exponentially take off, and then the birth rates and the death rates will pretty much even each other out, and your population growth will level off. That type of a curve is a logistic population growth, logistic curve, which is really a special form of the Bernoulli differential equation when we model population this way. How do we go about doing it? Well, let's say we let A, which is a constant, and again, we're going to make some assumptions here for our population growth. Let's let A be the average birth rate of our population. Now, average means you're going to take births per person. Take the total number of births divided by the total number of people, and you'll get the average birth rate. which we're going to assume that's to be a constant greater than 0. All right? And then we're going to make another assumption. We're going to assume that the average death rate, which we'll call it D, is proportional to the population. The more people you have, the more crowding you have, the more impact the limited food will have on the population, so your death rates will be proportional to the amount of population. If that's the case, then your death rate is proportional to the population, or death rate is equal to some proportionality constant, which I'll call B, times your population. B is just a proportionality constant. A is your average birth rate. D is your average death rate. And thus, the rate of population change in your total population per person, this is actually asking for the average population change. The average population change, which is the rate of population change per person, would be the rate of population change per time, right? The rate of change of the population with respect to time, divided by the total population, should equal the average birth rate minus the average death rate. Average birth rate is A. Average death rate then would be this BP. So it's minus BP. If I multiply both sides by the population, I get a differential equation. The rate of change of P with respect to time is equal to AP minus BP squared. This is a Bernoulli differential equation. It's a logistic differential equation. And we're obviously subjected to an initial condition. To solve this differential equation, obviously you're going to get first derivative. After you integrate, you're going to get an integration constant, so we need one condition to get rid of that constant. And we're going to subject this differential equation to the population at time equaling 0 will just equal our P sub naught, which is our initial population, whatever population we started with. Okay? Now, something you need to know about this equation. Notice the rate of change of the population with respect to time is really a function of two things. It's a function of A, which is the average birth rate, how many births you have. And then obviously you're subtracting out a term that has BP in it, which is, obviously has to do with your death rate. This last term, which is what slows down your population, right, minusing, slows down the rate. This is called a competition term. The competition term, because this is the thing that's competing, this is where you have population competing for resources, hence slowing the population growth down. Slowing the population growth. If you did not have any deaths, did not have this competition term, then you would have just the rate of change of P with respect to time is equal to AP, A being a proportionality constant, and this would be exactly analogous to what we did last time with the radiation. This would be a population that would grow exponentially. You get a simple exponential growth, and you would grow on forever, wouldn't you? But this term is what brings it down to life. So how do we go about solving this? Now, we talked about solving this before. I'm going to separate the variables. BP over, and I'm just going to divide this quantity on the other side, and you'll get AP minus BP squared equaling, and then what do you have on the other side? DT. That's a separation. You integrate both sides. You obviously on this side get T plus C. And this side, how do you handle it? Talked about it before. What do you have to do?
Partial fraction.
Right, partial fraction decomposition. Factoring out of P, A minus BP, and you have a partial fraction ordeal. And again, once you integrate, you'll subject this to this condition. Time 0, the population is P sub naught. You should solve that. And for this particular case, this is going to be your solution. Oops. That's your solution to this particular differential equation. And if you graph that for a given initial population with a given birth rate and a given proportionality. Can I see it's still a function of B, which is the proportionality constant between the population and your death rate. You will find that this will look like this. You'll exponentially take off and then you'll decay over time. Or actually you'll level off during time. There's actually a horizontal asymptote that you will be approaching. And you can find the horizontal asymptote. How would you go about finding the horizontal asymptote of this thing?
T, is the limit T goes into infinity?
Yeah, you just take the limit of this quantity as t goes to infinity. If you let time go to infinity, you're going to see what your population will level off to. And if you let time go to infinity, what's your population going to? This is going to what? If you let this go to infinity, right? It's going to 0. So what do we have here?
Your two rates,
A over B.
ratio of the rates.
So that's really going to be, you know, your P equaling A over B is that horizontal asymptote. Okay? Let's take an example of this. Let's actually work an example. And again, this is a nonlinear case. Why is it nonlinear? Because it is a Bernoulli. You have your P squared. This is a linear, this is a differential equation, ordinary differential equation of order 1, first derivative, in P, but it's nonlinear because you have a linear derivative, you have a linear term here, but you have a square term here, nonlinear in P here. Let's take an example. Let's say let me get you an example here, 135. All right. I think I talked a little bit about this, that rare infectious disease that's going around. Did you read it in the paper last night?
Tiliatis or something
Yeah.
like that? Yeah.
Remember that? All right. You got some professor walking around campus here. You got to be careful for this with this guy. He has tiliosis. And he teaches differential equations. Teaches 100 students. This professor is infected. All right? Actually, he's infected with the worst strain of tiliosis, and that's tough love tiliosis. The disease. The disease spreads. Disease. Spreads at a rate proportional to the students, to the number of students. That are infected. And so it's a joint proportion, and to the number of students that are not. After 3 days of teaching, there are 8 students infected. I want to determine the number of students infected after 1 week of teaching, 7 days. And obviously I'm assuming that none of these students drop the course. They get infected, they pass it on. All right, now when you have a case, folks, where you have a rate of change of the disease, obviously the rate that the disease spreads, which is going to be the change in, we'll call it T for tiliosis, with respect to time, when that is proportional to the rate to the number of students that are infected and to the number of students that are not. Perfect case for a logistic problem. What does this mean? This is proportional to, actually I'll just say x. Let x be the number of infections. So the rate in which the disease spreads, the rate of change in the number of infections with respect to time, is proportional to, and I state here, it's proportional to the number of students that are infected. Number of students that are infected is x. Times, because it's a joint proportion, to the number of students that are not. Well, how many students are not? If you have a total of 100 students, you'll have 100 minus x would be the amount of students that are not infected. Right? Number infected, number not infected.
And what about the professor?
I'm not one of the students. Yeah, because at time equaling 0, what's x? 1. So we'll just say there's 99 students. I'm one of the students. I'm always learning when I teach this class. Students and prof. Smarty pants. You're sitting in the back. You're supposed to be quiet. Okay, so we have a time equaling 0. There's only one infection, right? That professor. Here's my differential equation, so I can say that the rate of change of the infection with respect to time is equal to some constant of proportionality, x times 100 minus x. And x of 0 equals 1. I also stated after 3 days, so x at 3 days, what do we have? 8 students are infected, so x will be 8. And I want to know the amount of infections after 7 days. Right? Okay, so we just solved this differential equation. Did everybody see how I modeled the problem? This would be, again, separation of variables. Integrate, and you get this, the integral dx over x times 100 minus x, equaling kt plus a constant. So let's integrate that. All right, I'll do the partial fractions for you. I didn't do that last time, so I'll do it now. How many folks have no problem doing the partial fractions here? Don't need to see it. Maybe I should turn it around and get you guys active in the class. Say, how many of you folks need to see it? Nobody?
Yeah, go over it.
Okay, with that, we have time, unlimited amount of time in this class, right? All right, let's do the partial fraction decomposition for the folks that can use this. All right, you take this fraction, 1 over x times 100 minus x, and we'll break it up into our 2 partial fractions. And I need to find the constants a and b. Multiply through by the denominator, and you get 1 equaling a times 100 minus x plus b times x. And now I have to find a and b. I'm going to do it by judicious guessing. I'm going to let x equaling 0 in my first case. When x equals 0, a, you have 0 here, you have a 0 here, you'll have 100, a equaling 1, or a equaling 100th. And if you let x equal 100, this term cancels out, and you get b times 100 equaling 1, or b equaling 1 over 100. So this is actually, equal to the integral. The integral of this is equal to the integral of that, which is equal to what? 1 over 100 dx over x plus 1 over 100 integral of dx over 100 minus x. Integrating this, what do you get? You get 1 over 100 times the ln of x, and this would be, I'm factoring out the 100, what would this be? Can you integrate that? Minus the ln of 100?
Minus x.
100 minus x. And I could have a plus c, but I'm going to move the other c over here, just making one c. This can be written as 1 over 100 Subtraction of two laws, so I have the ln of x over 100 minus x. That's equal to kt plus c. I can write this as the ln of x over 100 minus x raised to the 100th equaling kt plus c, and we're going to exponentiate both sides. And what do we get when we do that? We get just x over 100 minus x to the 100th equaling c e to the kt. I can raise each to the 100 and just simplify this, write it like this if I wish. C e to the 100 kt. So now I have this equation. Again, you can try to solve for x. It's not necessary yet. We have a condition at x of 0, we have only one infection. So that means x is 1, so I have 1 over 99 equaling c e to the 100 times 0, or e to the 0, which is just 1, so you have c equaling 199. So this is x over 100 minus x equaling 1 over 99 e to the 100 kt. And then we can find k by our second condition, that at time equaling 3 days, we have 8 people infected. So we have x of 3 equaling 8. And just again, simplify it, substitute it in. Finding a particular solution to this differential equation. 1 over 99 e to the 100 k times 3. And you solve for k. And if you solve for k in this case, let's see if I have it here. Oh, this is a non-linear case, huh? We get k equaling 0.00718. So your differential equation ends up to be x over 100 minus x equaling 1 over 99. Or you can multiply that 99 on the other side. Let me do that. 99x e to the 100 times this is 0.718 t. And that's our model, logistic model of teleosis. So if I wanted to know how many people are going to be infected at day 7, I just plug t equaling 7, and I'll get 99x over 100 minus x equaling e to the 0.718 times 7. Solve that, and you get x equals 60 and a half students. So in 7 days, 60 and a half of you will be infected. Okay? I don't know how you infect a half a person. I guess you just start feeling it in this sinus cavity and not in this one, right? That would be a half infection. Does everybody understand how we model this? Okay, now this is a case of a nonlinear differential equation. A modeling of a problem forming a nonlinear differential equation that we would have to solve. Let's try one more example. This example is a very common example that they use in civil engineering. And we're going to take the case of a catenary. Catenary is a hanging cable, a static hanging cable that is essentially hanging under its own weight. So let's say we had some cable, let me draw it on a coordinate system. Here's x and here's y. And I have some cable hanging, like so. Okay? And I'm going to center the y-axis such that the y-intercept will intercept, obviously, the lowest point on the catenary, the sagging cable. All right, so right here is the lowest point. That's the lowest point of the cable. Now, if I wanted to mathematically try to model the shape of this curve, I want to find what y is equal to. This y, this obviously the shape of the curve takes on some shape, and I want to find it, y equaling some function of x. Well, I can find this just by knowing first this is a static case, meaning that the cable isn't moving, it's not swinging, it's not drooping, it's not tightening up, it's just sitting there under its own weight. We call this obviously a static case. We can use Newton's laws, second law of motion, to aid us in coming up with actually a curve shape for this catenary. So we're going to do a little physics here, see what we get. Let's say I take any point right here. Let's take some point on this cable. This point I'll call it xy. Let me call it over here, xy. This point obviously is the lowest point. There's a tension in this cable, just due to the weight of the cable and gravity. There's a tension at this lowest point because the tangent line is horizontal. You're going to get a horizontal tangent. A horizontal tension in the cable at the lowest point. Up here at any point xy, you're going to get a tension that's going to run tangent to the curve, right? So these are the two forces that are actually acting on this. Actually, you have a third force. You have the weight of the cable itself. Now we're going to say this cable from this point, and I'm only analyzing just a section of the cable, right? This cable obviously goes on. I'm only analyzing this one section and see if I can depict an equation for the curve of this catenary. I'm taking a section. This section has a certain arc length. So I'm going to say the length of this cable from here to here is just s. And that's a function of where I place my point. So it's a variable. And I'm also going to say this cable has a density. And this density, rho, which is a linear density, which means that there's so much mass per foot of cable, or per length of cable. This is measured in mass per length. So when you talk about a cable, you want to talk about the weight of a cable, you essentially size the cable based on its density. 5 kilograms per every foot, or 5 kilograms per every meter, or what have you, designates the density, linear density. If I wanted to get an expression for the weight of this section of cable then, wouldn't it just be the mass times the acceleration due to gravity? Right, that's the weight. And I can write this mass in terms of its linear density by the mass of the cable times the length. And what's the length of this section? S. So wouldn't this just be G times, or mass, which is rho times S times G? Rho S is the mass. That's your density times the length gives you the mass, right? This would be in kilograms per meter, and S would be then in meters. You get kilograms, the mass. So this is actually just equal to rho GS. So we have the weight of the cable is rho GS, and it's a variable weight depending on how long your section of cable that we're looking at is, right? S is a variable. Rho is a constant. It's something that you're given at the beginning of the problem. And G is obviously a constant. It's just the gravitational acceleration, right? 9.8 meters, negative 9.8 meters per second squared, or negative 32 feet per second squared. All right, so we know this weight. We know that there's a horizontal tangent at this point, and we know there's a tangent, a horizontal tension at this point, and a tangential tension in the cable at this point. Let's do an analysis on this. This tangential component, or this tangential tension, can be broken up into two components, right? You have I'll call that angle theta. you have a horizontal component of this tension and a vertical component of this tension. The horizontal component will be T cosine theta. The vertical component will be T sine of theta. Correct? And we know, because it's a static case, if I sum the forces in the x direction, and I'm also going to sum the forces in the y direction. If I sum the forces in the x direction, normally Newton's law says that the sum of the forces in any direction is equal to the mass times the acceleration. Use that back in 1.2. But in this case, is the cable accelerating?
No.
Cable's static, standing still. So there's no acceleration. So the sum of the forces in the x direction must be equal to 0, and the sum of the forces in the y direction must be equal to 0, because it's a static equilibrium. Well, if that's the case, what type of equations can come out of these two facts? This is Newton's second law. What comes out of these facts? Well, let's see. Let's sum our forces in the x direction. See what we get. If I sum my forces in the x direction, I have T cosine theta, and this is a minus h, right? That should equal 0, or T cosine theta must equal h. What do we get when we sum the forces in the y direction? That's T sine of theta minus rho gs should equal 0, or T sine theta should equal rho gs. In other words, this force up must equal this force down, this force to this direction, positive x direction, must equal that force to the negative x direction. For this thing to stand still, forces must all balance. So far, so good? All right, let's see what we can do with this. Again, what are we trying to do? We're trying to get some function y equaling some function of x out of this. Well, some things to consider in this problem. I also notice here that this is a tangent, this horizontal tension is tangent, right? That if I took the derivative of y with respect to x at x equaling 0, right here, this is x equaling 0, what should that derivative equal?
0.
Why?
It's the bottom of the arc.
Yeah, because the bottom of the arc, the slope of the tangent line to this curve at this point, what's the slope of this tangent line? M equaling 0, so the derivative of y with respect to x at this point right here should be 0, right? It's a critical point. Derivative should equal 0. Okay, keep that in mind. I'm going to take these two formulas, these two equations here, and I'm going to divide them out. I'm going to take t sine of theta and divide it by t cosine theta, which would equal rho gs and divided by h. This simplifies just to the tangent of theta, which equals rho g over h times s. Now the tangent of theta, which is this side over this side, right, is actually the rise over the run. It's the slope of this tangent. It's the slope of that tension. The slope of the tangent line is the tangent of theta. And we know that the tangent of theta, the slope of a tangent line, is actually the derivative of y with respect to x. Taking the derivative of the function with respect to x, you get the slope of the tangent line. Or taking the tangent, remember, rise over run will give me the slope of that tangent line. Hence, this is actually just the derivative of y with respect to x, equaling rho g over h times s. Now I'm getting it in terms of x's and y's. Still have an arc length in here. I am going to, instead of carrying this term around, I'm going to let this quantity right there equal 1 over a. Now I'll show you why it's 1 over a instead of a in a moment. So a essentially would be h over rho g. Keep that in mind, that's a, that's our first substitution. So that this just simplifies to the derivative of y with respect to x equaling s over a. Now folks, all I need to do is solve for that y in terms of x, and I'll have the equation of my curve. I'll have the function that a sagging wire, sagging cable will take on. And all I have to do is solve this differential equation. But we have not y on this end, we have an arc length. Remember back in Calc 2 what a differential arc length is? What is the differential arc length, what's the differential arc length equal to in terms of dx? Anybody remember that from Calc 2? 1 plus
dy dx
dy dx quantity squared. Right? This is how I relate the differential arc length to x's and y's. Or if I move the dx on the other side, I'll have that, wouldn't I? This is from Calc 2. Well, knowing this, and knowing that, I have an s here, if I can get this s into the derivative of s, then I can substitute this, and then I'll have s's turned into x's and y's, which is what I want to do in order to solve this differential equation. So my next step here is to take the derivative of both sides. We're taking the derivative of this side and this side, what do we get? We get the second derivative of y with respect to x is equal to, this is 1 over a constant, times the derivative of s with respect to x. And this now allows me to get rid of the arc length and get it in terms of x's and y's. So what's this equal to? 1 over a, the square root of 1 plus dy dx quantity squared. So we have this, obviously, nonlinear differential equation. You have the second derivative of y with respect to x equaling 1 over a, the square roots of 1 plus dy dx quantity squared. This is the differential equation relating y's with x's. This is the differential equation that will depict that shape of a hanging cable. Well, if I can solve for this, then I'll know what type of shape that cable is taking on. How do I go about solving this? Well, we did this before. This is one of the examples of a second order nonlinear differential equation. What did we do? Did anybody remember what we did? Oops, I didn't raise my hand. What did we do to solve that?
Substitution.
What did we substitute?
Dy dx for the constant.
Yeah, I just let dy dx, it's not actually a constant, but you let it equal to a variable, right? I'll let beta, for example, equal the derivative of y with respect to x. What that actually does is it simplifies this second order differential equation, reduces it to a first order differential equation. The derivative of beta with respect to x, and then is just equal to the second derivative of y with respect to x. Hence, substituting, you'll get the derivative of beta with respect to x equaling 1 over a, the square root of 1 plus beta squared. Now I have a separable differential equation, order 1. Let's separate this. Moving it over, I'll get d beta over the square roots of 1 plus beta squared equaling 1 over a times dx. I can now integrate both sides. Integrating both sides, what do I have here? We'll stay off just a few minutes, folks. I want to finish this problem.
Arctangent of beta.
No. Square roots of 1 plus beta squared, that's the inverse hyperbolic sine of beta equaling x over a plus some constant. Let's see if we can solve for this constant. Well, what is beta? It's the derivative of y with respect to x. And I know way over here a condition that at x equaling 0, what's the derivative of y with respect to x? 0. Which, isn't that equal to beta? So I can say here, at x equaling 0, beta, which equals the derivative of y with respect to x, is actually equal to 0. Gives me a condition. So beta of 0 equals 0. Let's plug that condition in here. If I plug this into here, you'll have beta equaling 0. You'll have the inverse hyperbolic sine of 0 equaling, and you're going to let x equaling 0. You'll just have c. Anybody know what the inverse hyperbolic sine of 0 is? This is the hyperbolic sine of what value gives you 0?
0.
Good. 0. Anybody know how the hyperbolic sine, how the inverse hyperbolic sine works? Anybody know? No? Looks something like that? Or did I have it wrong? No, that's right. So at 0, the inverse hyperbolic sine is 0. So you have 0 equaling c. So therefore, this now becomes the inverse hyperbolic sine of beta equaling x over a. Or beta equals the hyperbolic sine of x over a, getting rid of the inverse. And beta is equal to the derivative of y with respect to x. That's equal to the hyperbolic sine of x over a. How do I solve for y? I can separate, get dy equaling the hyperbolic sine of x over a, integrate both sides, dx, integrate both sides, and I get y equals, what's the integral of the hyperbolic sine?
Cosine.
Now remember, you have x over a, so if you let u equal x over a, du will equal 1 over a, so that would actually be a hyperbolic cosine of x over a plus some constant. Notice the form, notice the shape of a hanging cable. It's a hyperbolic cosine. Something that you should have learned, at least, not all of this, but you should have learned that hanging cables take on the shape of a hyperbolic cosine. Now how do we solve for this c? Well, that c is really an initial condition. It really depends on where I place my cable relative to my coordinate system. Now I'm going to make a substitution. Right here, I'm going to say that this cable, I place this cable such that this distance right here is A. What was A? H over rho G. In other words, whatever the horizontal tension is at that bottom of the cable, divided by the density of the cable, divided by the gravitational acceleration, whatever that quantity is, that's where I'm going to place my coordinate system such that the cable, the lowest point of the cable, is that high off the ground. It's A units or H over rho G units above the ground. I can really place my coordinate system anywhere I wish. Now watch, when I do that, something magical happens. So this is saying at x equaling 0, y is equal to A. And I place it there so I can get rid of the c, make it the simplest formula you could possibly make. If y is A, you get A equaling A, the hyperbolic cosine of 0 plus c. What's the hyperbolic cosine of 0? 1. So this is just A equaling A plus c, or c equaling 0. Therefore, if I allow my cable, the bottom of the cable, to be A units above the ground, A being this quantity, whatever this magical quantity is, then my equation for my catenary, I'll erase all this, equation for my catenary is simply y equaling, what do we have there? A hyperbolic cosine of x over A. Simplest form. Now remember, this is when the bottom of the cable is A units. We forced it to be A units above the ground. Now something magical happens at this height. If I had my cable that far off the ground, watch what happens. Let's say if I take this cable and I'm A units above the ground, the lowest point, and I take it, and there's a pulley here, and I run this cable, and I let the cable touch the ground. All right? This cable, we know we have a horizontal tension right here, H. If I wanted to calculate the weight of that cable, and obviously you have a tension going off like that, T. If you want to know and let's say the length of this cable is just Y. Y is the length of that unknown cable. If I want to know the weight, isn't the weight equal to rho G times the length? So it would be rho G, rho being the density, obviously, rho G, in this case, Y. Well, now let's look at our problem here. This is the equation of this curve. I know from our analysis, right here, let's take this right here, that T cosine of theta equals H. If I solve for T, I'll have H over the cosine of theta, which is H times 1 over the cosine is the secant of theta, Now watch how I algebraically force this into something of meaning. T equaling h. Secant, isn't the secant squared equal to 1 plus the tangent squared? So secant would equal the square root of 1 plus the tangent squared of theta. Trig identity. T then would equal h times the square root of 1 plus, well, isn't the tangent of theta the derivative of y with respect to x? So this would equal the derivative of y with respect to x quantity squared. Well, y is this function. That's the equation of this curve. So let's take the second derivative, or let's take the derivative of that. What is y prime? What's the derivative of y with respect to x if this is your equation? Well, you take the derivative of this. This would be a hyperbolic sine of x over a times 1 over a. Or just the hyperbolic sine of x over a. Then square it. You get the hyperbolic sine squared of x over a, don't you? Plugging that into here, look what I get, folks. Tension equals h square roots of 1 plus the hyperbolic sine squared of x over a. And what is 1 plus the hyperbolic sine squared? It's the hyperbolic cosine squared. H square roots of hyperbolic cosine squared of x over a, which is just t over h equaling, and I'll just write this as the hyperbolic cosine of x over a. Well, if you look at your original function, y over a, isn't y over a equaling the hyperbolic cosine of x over a? So I'm going to do a substitution. This quantity is just equal to y over a, isn't it? So I have t over h equaling y over a, or t equaling y times h over a. And what was a equal to? H over rho g. So you have y h over a, which is h over rho g. H's cancel, and you get y rho g equals the tension. And what was y rho g equal to? Y rho g was equal to the weight of the cable hanging over a pulley, all the way down to the ground. So this is saying that the tension in the cable can be eliminated, can balance out, if you have the sag, this magical distance off the ground, h over rho g, then no matter where you are on this cable, if you lopped it over a pulley, because you don't obviously want any friction there, but if you lop it over a pulley and you run the cable all the way down to the ground, the weight of the cable will be enough to balance the tension in the cable, hence that thing will stay just like it is. It won't sag anymore. Obviously, if your bottom, let's say if this were the ground, this was the ground right here, you're too short, what would happen? You don't have enough cable here to balance out the tension, and the thing's going to sag, eventually touch the ground, right? What happens if your ground is down here, where this is larger than A? Then you're going to have too much cable here, right? And this thing will tighten up. This tension would get tighter and tighter and tighter. In other words, your cable would slide. But the one point where the cable would balance is if the sag, bottom of the cable, is at this h over rho g, whatever quantity that is. Then you can just hang a cable over, touch the ground, and that will stay just like that. This will balance out any tugging on this cable, if the cable wants to sag or get taut. This is necessary, this proof is necessary, or this derivation, this modeling is necessary, for when they hang cables on telephone poles. What do we want to do? We want to make sure that the tension in the cable between telephone poles balance. Well, if I have a tension, I know that if this is at a certain height, this special height, then that's the amount of cable I need to wipe out this tension and keep this in a static equilibrium. No torquing on the telephone pole. So the next cable, I just have to make sure that the weight of the cable coming off of this thing is that long. They usually try to put telephone poles between the length of the telephone, the height of the telephone pole, and again, they want it, because you got to balance out this to the next telephone pole. So half of this weight right here has to be this length. So in most cases, when they lay telephone poles, they try to be as close to two times the length of the telephone pole before they put another telephone pole. Just so that the cable, half the cable balances out with this tension. This half balances out with the next tension, and so forth. Does everybody understand that? So you'll see, rule of thumb, if the terrain allows it, they will try to place a telephone pole at twice the length of the telephone pole. Just because you obviously don't want any torquing on this telephone pole. You don't want your telephone poles to be sagging this way over time or this way. All the weight then, if these weights cancel, all the weight is directed downwards into the footing. You have a balanced system. Ramesh? What's the identity? Because it's a minus cotangent of psi 1. But look up the identity. What's the tangent of two angles? Anybody have it? Do I have it? No, I just have the minus cotangent of psi 1. If you use the identity, which is right there, you can go back. Oh, no. Anybody have any identities with them? Trig book, or I mean a calculus book with you. Well, that's what it is. The expand, and I think it's the tangent of
Tangent of psi 1
minus,
plus.
or is it plus?
It's a minus.
You got it there?
It's a plus, yeah.
This is tangent of a plus b. Tangent a minus b is minus plus, yes. So it's a tangent of that plus the tangent of pi halves over 1 minus
Yeah.
the tangent of pi halves times the tangent of psi 1. Is that correct? What's the tangent of pi halves? What's the tangent of pi halves? Here's a tangent, folks. Right? Is that the tangent?
Yeah.
Isn't it undefined at pi halves?
Yeah.
That's why we can't use this identity. That's why I didn't do it that way. If you look at pi halves, if you look at psi, if you take an angle, psi, and here's your angle psi, and you add pi halves to it, 90 degrees. This is the angle psi 1 plus pi halves. Is the tangent of this angle equal to the negative cotangent of psi 1? Which is equal to a negative 1 over the tangent of psi 1, which then I can move this on the other side and get the tangent of psi 1 times the tangent of psi 2 equaling a negative 1. This is what we can use for orthogonal trajectories. Notice how similar this is to m1 times m2 equaling a negative 1. Although these don't represent the slopes of, these do not represent the slopes of the tangent line. It's just a quantity, tangent of this angle times the tangent of this angle has to give you a minus 1. Now we can use this simple identity, or simple expression, to prove whether, to determine whether two polar curves are orthogonal trajectories of each other. The problem is finding these angles. These angles aren't always easy. If I give you some r of theta, or r2 of theta, and then you have to draw a radial line and you've got to try to work out angles to the tangent, it's a very difficult thing to do. So the idea here is to take this expression and try to simplify it even further. Try to find some relationship of psi as a function of r and maybe the derivative of r with respect to theta. If I can write psi in terms of r and the derivative, then I'll have a real simple way of working this formula. Because is it easy to take derivatives of these functions? Sure. And you have the functions given, so r and their derivatives will be an easy thing to be had. Let's see if we can come up with some simple relationship. Taking this, I'm going to write this over here. Tangent of psi 1, tangent psi 2, equaling a negative 1. And let's try to find a relationship between psi and the function and its derivative. Let's take an arbitrary polar curve. Let's take a polar curve, something like this. This is r equaling r theta. If I drew a tangent line to this curve, let's draw a tangent line like this. And I'm going to extend the tangent line so that it actually crosses the x-axis. Here's my tangent line. My radial line would be like so, and I'm going to extend the radial line. This is my radial line. And then this angle right here would be psi, wouldn't it? The angle from the radial line to the tangent. Well, I also see here that the slope of this tangent line in a rectangular coordinate system is the derivative of y with respect to x. So if I wanted to take, let's draw an altitude down here. This angle right here is theta, right? Because you go theta out, this is r, theta and r to get to that point, that's r theta. If this is psi, this angle right here is psi, right? Vertical angles. And let me call this angle right here alpha. And isn't the slope of the tangent line equal to the change in y, or the dy over dx? In other words, I can write this little section right here as dx. This is the rise over the run. That gives me the slope of the tangent line. Does everybody see that? This is my tangent line right here. So I can say that the tangent of this alpha is equal to dy dx, which is the slope of the tangent line. Now, I can relate alpha, this angle, to these two angles. What's the relationship between alpha, theta, and psi? Anybody? See this triangle right here? A triangle. This is an exterior angle. What's the exterior angle of a triangle is equal to what? The sum of the two remote interior angles. In other words, you have alpha equals theta plus psi. Think of it. This plus that angle has to equal 180 degrees. This plus that angle has to equal 180 degrees. Do a substitution, you get this angle has to equal this plus this. So if I take the tangent, well, let me solve for psi here. I get psi equaling alpha minus theta. Now, again, I'm trying to find some relationship for the tangent of psi and somehow relate it to r's and dr d thetas. And I'm going to do it through this. I'm going to take the tangent of both sides. And then I'm going to use the identity. And what was that identity again? You got the tangent of alpha minus theta. I think it's tangent of alpha plus the tangent, or minus the tangent. Check me on this. Over 1 plus the tangent of alpha, tangent of theta. When you have a minus in here, isn't the top minus? Is that correct? Plus down here? You're the expert.
Yeah.
You got the sheet. So this is equal now to the tangent of psi. Well, what is the tangent of alpha equal to? If you notice, this is the alpha, tangent of alpha is equal to dy dx. So this is going to be written as dy dx minus the tangent of alpha over 1 plus dy dx tangent of alpha, a tangent of theta. I'm sorry, dy dx minus the tangent of theta over 1 plus dy dx tangent of theta. This equals the tangent of psi. Now, dy dx. Again, this is a rectangular coordinate business. I want to get this into polar. At least with my curve r equaling r theta, can't I write this in parameter form and say that this is really x equaling r cosine theta and y equaling r sine of theta? And this will now allow me, and remember these r's are functions of theta, so it's a product rule when you take the derivative. And this is going to allow me to go from the derivative of y with respect to x to derivatives of r's with respect to thetas and r's. So let's find what the dy dx is. And I did that for the other example. Go off to the side here. Actually, I'll do it over here. What was dy dx equal to? Well, that was equal to dy over d theta over the derivative of x with respect to theta. And what was the derivative of y with respect to theta? Using the product rule, you'll have r cosine theta plus derivative of sine is a minus r prime cosine theta. No, that's not right. R's no, right. First times derivative of the second cosine theta plus the second times derivative of the first. All over, what's the derivative of y? Or derivative of x with respect to theta? That's going to be first times derivative of the second plus the second times derivative of the first. Right? Does everybody see that? Now I'm going to take this, unfortunately. I'm going to take this, and I'm going to plug that into here, and I'm going to plug it into here, and see if I can simplify this mess. Who asked to have this done? Which one of you? Tangent of phi, tangent of psi equals, what's the derivative? Let's write it out. You got r cosine theta plus r prime sine theta over r prime cosine theta minus r sine theta. Right? Minus the tangent of theta, which I'm going to write as the sine of theta, over the cosine of theta, all over 1 plus the derivative again. That's r cosine theta plus r prime sine theta over r prime cosine theta minus r sine theta times the tangent of theta, which is the sine of theta over the cosine of theta. And now I have to simplify. Well, I look at this and I see there's a common denominator here, folks. What if I multiply this quantity and this quantity by the common denominator? And the common denominator is going to be cosine theta times r prime cosine theta minus r sine theta over cosine theta times r prime cosine theta minus r sine theta. Right? Isn't that the common denominator? Boom. That quantity is the same as this quantity. Right? Cosine. Right? Everybody got that? And if I multiply this out, what do I get? I get this quantity times that first quantity minus, this is going to cancel out with this common denominator. So what's the common denominator here? If I multiply this by cosine theta, multiply this by, just multiply it out. I'm trying to find a way to get around it. Tangent of psi equals what? This quantity times this quantity. You can see this denominator cancels with this. You just get the cosine of this, cosine times this, so you get the cosine of theta times r cosine theta plus r prime sine theta minus these two quantities multiplied out gives you what? Cosines cancel, you get sine of times this. Sine of theta times r prime cosine theta minus r sine theta. Now, obviously, you don't have to go through this nonsense every time you want to do this. Hopefully, this will reduce it to something simpler than what we had before when we took the two slopes and multiplied them together to get -1. This times 1 gives me the cosine of theta times r prime cosine theta minus r sine theta plus this time, oh, I'm sorry. Yeah, is that, yeah, that's right. And then this times this quantity, what cancels? You got the cosine canceling, and you got this quantity canceling. So you're just gonna have that quantity. The sine of theta times r cosine theta plus r prime sine theta. Let's see what we get. Let's multiply it. Let's see if it's our lucky day. Multiply this out, you get r cosine squared theta plus r prime sine theta cosine theta minus, this times this gives me minus r prime sine theta cosine theta plus r sine squared theta over, multiplying all that out, you get r prime cosine squared theta minus r sine theta cosine theta. And then this times this gives you a plus r sine theta cosine theta. This and this gives you a plus r prime sine squared theta. And you see, this cancels with that. This cancels with this. let me erase this. I have now the tangent of psi equaling, you have r cosine squared theta plus r sine squared theta, which is r times cosine squared theta plus sine squared theta, over, and here you have the same thing. You have r prime cosine squared theta plus r prime sine squared theta. So this gives me r prime cosine squared theta plus sine squared theta. Those are both 1 and they cancel, giving you just simply r over r prime. And that's equal to the tangent of psi. See, God is on my side. Now, folks, wasn't the case, where did I, yeah, right here. We wanted to use the tangent of psi 1 times the tangent of psi 2 equaling a negative 1. That's what we proved, what we found had to be the case to prove that two polar curves are orthogonal trajectories of each other. Well, the tangent of any psi is r over r prime. So I can say that the tangent of psi 1 times the tangent of psi 2 will just be r1 over r prime 1 times r2 over r prime 2. And what does that have to equal? Negative 1. So this is now the relationship for orthogonal trajectories in polar. Or better yet, let's move these on the other side and I'll get r1 times r2 has to equal a negative r1 prime, r2 prime. In other words, take the two functions, multiply them together, and it has to give the negative of the two derivatives multiplied together. Or, if I just flip this on the other side, I'll get r1 over r prime 1 equaling a negative r2 prime over r2. This ratio of r over r prime, negative reciprocals of each other. It's not their derivatives. R prime over r or r over r prime, it doesn't matter. This ratio between two orthogonal polar curves are negative reciprocals of each other. In rectangular coordinate systems, it was just the derivatives are negative reciprocals of each other. Here you have to take the derivative and divide it by r, and then you would have the two curves are negative reciprocals. This quantity are the negative reciprocals of each other. Do you understand? So if I wanted to find the two polar curves or negative or orthogonal trajectories of each other, I would find this quantity for each polar curve. R prime, I would take the derivative. Now remember what this is. This is the derivative of r with respect to theta, and divided by r. So you take the derivative of the function with respect to theta, divided by its own function. Do that for both of them, and they should be negative reciprocals of each other. That if you took both and you multiplied them together, you'll get a negative 1. You understand? Almost identical to what it is in rectangular coordinate system, but we had to go through it a little bit more hairier derivation. So let's take an example. So as far as you're concerned, on your end, it's a piece of cake. I'm the one that had a sweat. Let's take an example. Let's say if I wanted to see if two polar curves, let me take two. If two polar curves are orthogonal trajectories of each other. Show that R1 equaling 2 cosine theta and R2 equaling sine theta are orthogonal trajectories of each other. Now remember folks, you could use the fact, find the derivative, find this dy dx for each of these. Find the derivative of y with respect to x for each of these. In other words, take this, write this polar curve in terms of a parameter form, right? Write this in terms of its parameter form. Then take the derivative of y with respect to x of both of these, and then those two multiplied together must be a -1. Or you can stay in polar and say r over r prime, or r prime over r, doesn't matter which way you do it, have to be negative reciprocals of each other. So I'm going to find r prime 1 and r1, and if I multiply it by r prime 2, wrong way, r prime 2 over r2, that should give me a -1. So for each r, I'm going to find the ratio of its derivative over the function. Multiply those two together, if I get a -1, they're orthogonal trajectories. So let's do that. What's r prime of 1? Take the derivative of this is the derivative of r1 with respect to theta, which is what? -2 sine theta. And obviously r1 is equal to 2 cosine theta. So what is, put these together, I'll put it over here. What's r prime 1 over r1? -2 sine theta over 2 cosine theta, which is just a negative tangent theta. Right? Let's do it for the other curve. I'll do it in purple here. What's r2 prime? Cosine theta. And r2 is equal to the sine of theta. Put r prime 2 over r prime, r prime 2 over r2. And what do you get? Cosine theta over sine theta, which is the cotangent of theta. Are they negative reciprocals of each other? So if I took the negative tangent of theta, times it by the cotangent theta, let's see what I get. This is obviously a negative tangent theta times 1 over the tangent of theta, gives me a -1. They are orthogonal trajectories of each other. Okay? You follow? So it's the ratio of the derivative over the function that are negative reciprocals of each other, not just the derivatives, like the Cartesian coordinate system. All right, now let's take another example. Let's say if I wanted to find, let's say I had one curve, polar curve, and just like I did in rectangular coordinate system, I want to find another polar curve that is an orthogonal trajectory of the given one. Okay? See how I'm going to handle this. And we're going to handle it pretty much the same way we handled the example that I did in rectangular coordinates. Let's say I wanted to find the orthogonal trajectory of r equaling c times 1 minus the sine of theta. That means I'm given a polar curve. Matter of fact, is this one polar curve? It's a family of polar curves, right? Where c is a constant. So I have a family of polar curves, just like I had a family of curves in rectangular coordinate system. I have a family of polar curves, and I want to find the orthogonal trajectory of this family. Maybe one curve, it may be many. It will be another family. How do I go about doing that? Well, let's first find that ratio of r prime over r for this polar curve. Use the fact that this has to be the negative reciprocals of each other for each curve. What is the r prime for this one? If we take the derivative of r with respect to theta, this is going to be a constant, which is 0, and you have a minus cosine theta, right? Over this, which is c times 1 minus the sine of theta.
Do you have a C?
Oh, I'm sorry, there's a c still in there, isn't there? Which the c's cancel. So there. Okay, so we have a minus cosine theta. Actually, let me write it like this. Cosine theta over sine theta minus 1. Get rid of that minus. Okay? Now, folks, what do I know? This is we'll call this R1. Here's R1, R prime 1, and R1. What do you know about R prime 2 over R2, the one I'm trying to find? What must that ratio be equal to? The negative reciprocal of this one, isn't it? So how do I do the negative reciprocal of this? Negative, and you flip it over, right? Which is 1 minus the sine of theta over cosine. So that must be this ratio of our new family of polar curves that are orthogonal to the original family of polar curves. Do you understand? Now I have a differential equation here, folks. I have to solve this. This is, let's go r prime, which is the derivative of r with respect to theta. And I'm going to multiply this side by r2. You get equals 1 minus the sine of theta over cosine theta. And I'll do this, 1 over r. And I have to solve this. I can solve this differential equation. Everybody understand this is r prime over r? Right? R prime is the derivative of r with respect to theta over r. How do I solve this? Separate the variables. I can multiply this by d theta, and I'll have dr over r equaling 1 minus the sine theta over the cosine theta, d theta. Integrate both sides, and I have the ln of r equals, I got to integrate that wonderful thing. What's 1 over the cosine? Sine over the cosine, which is the tangent of theta, d theta. So I got to integrate those two. Anybody recall how to integrate the secant? From Calc 2? My mic? Speak up. Come on, speak. If I multiply this by secant theta plus tan theta over secant theta plus tan theta, you get a simple u substitution. Do you recall that from Calc 2? And if you let u then equal the denominator, du will equal the numerator. So this just becomes, and I'm just going to skip here and get to the chase here. This is just going to become the ln of the secant of theta plus the tangent of theta. That's the derivative of that. I mean the integral of that. Minus, how do you do the tangent? Yeah, leave it as a sine of theta over the cosine of theta, d theta. And I'm going to let u equal the cosine theta. du will equal a negative sine of theta, d theta. So they're just going to get a minus ln of the cosine of theta plus c. And again, you should be able to integrate those. This is the ln of r equaling, these two could be combined as the ln of secant theta plus tan theta over cosine theta plus c. Pardon me? This? Oh, I'm sorry, there's a minus already there, huh? Oops. Scratch that, folks. I saw a minus in here. You have a minus tangent. When you integrate, you'll get this will actually be a minus the ln of the cosine of theta. that what you're referring to? Yeah. So this is going to be a plus here. So this is going to be ln of r equaling the ln of secant theta plus tan theta times cosine theta. It's the ln of all that quantity plus c. I'm sorry?
1 plus sine.
Yeah, what's the sine, what's the secant times the cosine? Equals the ln of, these are reciprocals, that's just going to give you a 1. And this is the sine over the cosine, cosines cancel, you get plus sine of theta plus c. Now folks, you could do this. Again, I can exponentiate both sides. I'm going to erase this. I can exponentiate both sides, or I can write this constant. Sometimes you'll see this happening, and I just want to do this one time. I'm going to write that constant as an ln of a constant, which is still a constant, and then write this as the ln of, because you're adding logs, you can say the ln of c times 1 plus the sine of theta equals the ln of r. So if you exponentiate those two sides, you'll get r equaling c times 1 plus the sine of theta. You could have also left it just as a c, and when you raised it both sides to the e, you'll have e raised to the c, which is just a constant that goes out in front. This is now the polar curve, family of curves, that are orthogonal trajectories of the given one. We had to do it through a differential equation. We had to actually solve this differential equation by separation. Let's check it to make sure that we did all our integrations correctly. And I'm going to check it right here. In order for this, and I'll write it right under here, R2 to be c times 1 plus the sine of theta. Is that what I got over there? Yep. In order for those two to be orthogonal trajectories of each other, what must be true? What must have to happen? R prime 1 over R1 times R prime 2 over R2 must equal negative 1. Or if I find, notice this ratio, I already did it for R1. This is for R1. All I have to do is for R2 and see if in fact I get the negative reciprocal of this. So what is it for R2? That's R prime 2 over R2. And what's the derivative of this with respect to theta? That'll be 0 plus c cosine theta over c times 1 plus sine theta. C's cancel, and I simply get the cosine of theta over 1 plus the sine of theta. And you notice, are they negative reciprocals? Hard to tell right now. So what I'm going to do is I'm going to multiply the two, and what should that give me? So if I took the cosine of theta over 1 plus the sine of theta, and multiplied it by the cosine of theta over sine of theta minus 1, and pray that I get negative 1. If I get negative 1, I quit. This gives you cosine. No, I'm just teasing. I won't quit. You all sound so worried. Over, multiply this up. You get sine. You get a minus sign. What is this? What is it? You get sine theta minus 1 plus sine squared theta minus sine theta. These cancel, and you get the cosine squared theta over, you get sine squared theta minus 1. Sine squared theta minus 1, isn't that equal to the cosine squared theta over a negative times 1 minus the sine squared? And what's 1 minus the sine squared? So you get a negative cosine squared theta over cosine squared theta. There it is, negative 1. So in fact, they are negative reciprocals of each other. Capiche? I could stay. I don't have to quit. All right, does everybody understand? Orthogonal trajectories. It's one application of differential equations of order 1. Ordinary differential equations. Any questions on this? Let's look at some other applications. Let's look at some applications of linear differential equations of first order. We'll just do a few examples. And then we're going to move into applications of nonlinear first-order differential equations. And these are physical applications that we're going to use, we're going to do. Applications of linear first-order differential equations. And many things in life, folks, you're going to find that when we're trying to model natural phenomena, there's many cases where the rate of change of the quantity is proportional to the quantity itself. This happens all the time in nature. For example, in population growth, you'll find that the more people you have, let's let X equal the population, that the growth of the population is proportional to the amount that you start with, the amount of population you have. The more people you have, the faster the population grows. Why? Because you have more people to procreate, right? So, population growth, simple population growth, and this is population growth that has no constraints on it, grows according to this relationship. You have radioactive decay, for example. You have radioactive decay that pretty much follows this line of thought. That if you have a certain quantity of a radioactive material, everybody understand what radioactive decaying means? You have a particular material, let's say if I have, for example, plutonium. Plutonium won't stay plutonium forever. Because it's radioactive, it's breaking down into its daughter products, meaning that it's actually, the atoms are breaking down into other elements. Hence, you don't have any more plutonium over a very, very long time. Well, the rate in which a material is decaying, disintegrating into other elements, is proportional, that's this, the rate of the decay is proportional to the amount that you have. If I have a whole bunch, the rate of that decay will be a lot, will be great. If I have very little, the rate in which it decays will be small. Cooling. If I had if I heated up an object, and I set it on, and I just threw it on my desk to cool, the way that cools follows something similar to this. The rate of cooling is proportional to this would be, in this case, it wouldn't be X, it would be T. The rate of cooling, the rate of change of the temperature with respect to time, that's the rate of cooling, is proportional to the temperature. The hotter it is, the faster it will start, faster it will take off cooling. The closer it gets to room temperature, the slower it cools to room temperature. Obviously, you can't have objects cooling further past room temperature, right? If you find something like that, let me know. You and me will make a bunch of money. Okay? Breaking all laws of thermodynamics and being called frauds and crazy and loonies, but I'll find a way to make money off of it. All right, so there's many things in real life that follow this type of rule, physical rule, that the rate of change of an object is proportional to the quantity that you have. Now let's take some of these examples. Even some chemical reactions. The rate in which the chemical reaction occurs is proportional to the amount of reactants that you have. If you mix a bunch of chemicals, you're going to get a faster rate of reaction than mixing only a small amount. Let's take some examples. Let's take a radioactive decay. Radioactive decay problem. Let's say I had a breeder reactor. Everybody know what a breeder reactor is? Breeder reactor is a reactor that's, its sole purpose is to take uranium and turn it into plutonium. A breeder will actually take uranium-238 and change it into plutonium-239. 238 is obviously what? Anyone know what 238 is? That's the atomic number, right? And 239 is the atomic number here. You know why there are actual breeder reactors around? What's the benefit of taking uranium-238 and turning it into plutonium-239? Pardon me? No. This type of stuff is the stuff that they put in reactors for energy, but when they refine it, kick it up into this is with the stuff that they make weapon grade material, radioactive material. Okay, so we have breeder reactors around. Also, there are some nuclear reactors that will actually run on plutonium. Anyways, we have a breeder that's breeding this stuff. Okay, it's in my backyard, and I'm breeding this stuff. Don't tell anybody. Shh. Don't tell anybody. I don't want anybody knocking at my door. And after 15 years, I have a whole bunch of this in my backyard. Now, a whole bunch. How much is a bunch? If you had a pound of this, you'd be visited by many, many, many people in dark suits. Guaranteed. From all over the world. After 15 years, this amount of plutonium disintegrates. And let's see, how much do I have? I only have 0.043% of my initial amount. Which I'll call my initial amount A sub naught. So at time equaling 0, A sub 0 equals, or A of 0 equals A sub naught, where A equals the amount of plutonium-239 I have in my backyard. Now, you all need to write that down on your paper. So if any of you give me any trouble, I'll just call the right people and say, look at his notes. And you all confess that you have a whole bunch of plutonium in your backyard. All right, after 15 years, 0.043% of whatever I started with decays, disintegrates. I lose it. It's not, I don't have the same amount. It's like the money in my pocket. I could have 20 bucks. I have kids, folks. I could have 20 bucks, and within minutes, it's gone, it's disintegrated. It's radioactive, kid reactive. All right, and then we'll say, I want to find the half-life of the plutonium. Everybody understand what half-life is? Half-life means that if I started off with a pound of a radioactive material, this radioactive material is decaying, it's disintegrating. It's becoming less and less. I'm having less and less of this radioactive material because it's decaying into other elements. So if I had 10 grams, for example, of this plutonium, how long would it take for that 10 grams, for half of the 10 grams to disintegrate away? That's a half-life. The amount of time it takes for half of your radioactive material to disintegrate away. Now the thing about half-lives is if I had, for example, 10 grams of plutonium, and the half-life you'll see in this example, half-life of plutonium is about somewhere around 24,000 years. So I don't have to worry about it in my lifetime. The stuff that I have in my backyard, it's going to be there when I get home. Actually, I'll tell you an interesting story about plutonium. Plutonium is very radioactive, but it has a mean path of about a yard. Meaning that the neutrons that are kicking off, which is where the radioactive products that come out of the plutonium, the neutrons shooting everywhere. Neutrons are nice and big, right? As far as an elementary particle is concerned, neutrons and protons are the same size. So you got these neutrons spitting off, and then again, if you were holding a bunch of plutonium and say, "Ooh, my plutonium, nice plutonium," that plutonium would be reciprocating its love by bombarding you with neutrons. And those neutrons would go right through your body, hitting all the water molecules in your body, and you got a lot of those, a lot of hydrogen, and be transferring its kinetic energy into your hydrogens, into your water molecules. And you'd be like microwaving your internal organs by saying mine, all mine, right? So these neutrons, that's radioactive poisoning. That's how you die from radioactive materials. It pretty much cooks you from the inside, rips apart your cells, heats up cells so cells explode because they're boiling, because of all of that heat transfer. That's all it is. It's really just, think of it as a real fast, very small ping pong ball. Ripping through your body, heating you up inside, and killing you. You're dying that way. That's all radioactive material is. Nothing big, nothing scary. It's not mystical. But these neutrons, because they are big, and thank goodness we live in air, and water vapor, neutrons from plutonium can only travel about a yard before they pucker out and die. Okay? So if I were going mine, oh mine, you'd be safe. You could say, yours, all yours. Right? And I don't have to share it. You're not going to get sick. Because it only has a path, like a mean path of about a yard. Well, we had some of this plutonium when I was going in grad school. We were dealing with this stuff in the lab, doing experiments with plutonium, because he had nothing else to use, right? So we take a little bit of plutonium. And I had this one lab partner, brilliant guy, but a little strange. I'm telling you. I won't disclose his name, but he's probably a high-powered government official by now. But he's a little strange. He took this plutonium, and you have the lead gloves on, something that'll stop the flow of neutrons. And he picked it up, and he would walk around the dorms and camps. And hey, look what I got! Hey, what do you got there? Plutonium! Whoa! What the heck? Yeah, here, look. You want to see some plutonium? And he'd walk around, woohoo! I'm the king of the world, carrying his plutonium around. Like I said, he's probably behind some government official. He was smart because he made sure his arm was a yard long, keeping it, never went like this, always kept it like this, but he wasn't afraid to say, look! What a friend, huh? All right? Anyways, off the subject. We want to find the half-life of plutonium. In other words, the amount of plutonium I have in my backyard, I want to know how long it's going to take for half of that stuff to disintegrate. Okay? If I had to calculate this, it's radioactive decay. That means the rate of change, or the rate of decay, when A is the amount of plutonium I have. This is proportional to the amount of plutonium that you have. So the speed in which which plutonium decays is proportional to the amount of plutonium that you have. This means this, where K is your constant of proportionality. There's a linear first-order differential equation, a simple one. Now, how do we solve this? Well, I can separate the variables. And again, this is subject to some initial conditions. That at time equaling 0, the amount of plutonium that I have is A sub naught. Also, I have a second condition. The second condition is that the second condition is that A at 15 years is equal to how much of the original? Well, if I lose, this amount of this decays. This is the amount that I lose. So how much do I still have then? 0.9, no, actually this is percent, so 0.004, oh, 2 zeros. 0.00043, 1 minus that quantity, what is what? Somebody figure it out. No, it's 5.8, 5.7. Do I have enough nines? So at 15 years, A of 15 is 0.99957, the amount of my original, right? Right? All right, and I want to know, at what time, this half-life, will I have how much? If I start off with A sub naught, how much will I have if I let time go 1 half-life? Yeah, 1/2 A sub naught, correct? That's pretty much my problem. I want to find this time. All right, let's solve this differential equation. I solve it by separating the variables, dA over A equaling k dt. Integrate both sides. This becomes the ln of A equaling kt. Or exponentiate both sides, or write this in the exponential form. You get A equaling, kt plus c. Exponentiate both sides, you get A equaling e to the kt plus c, which is e to the kt, plus or times e to the c, which is a constant in itself. So you get A equaling c e to the kt. We have a constant here, which is a constant of proportionality, and we have a constant here we have to find. Well, I can find c by using my initial condition. I know that at time equaling 0 is equal to a sub naught. So if I plug time equaling 0 into here, I get a sub naught equaling c e to the 0, or c equaling a sub naught. So this constant of integration turns out just to be my initial amount. Does everybody understand? So this now becomes A equaling a sub naught, e to the kt. What do you think that second condition is needed for? Define k. That really defines how fast. That's one test point of how fast this radioactive decay is occurring. At time equaling 15 years, so at 15, I have 0.99957 a sub naught. So I'm going to write down 0.99957 a sub naught equals a sub naught e to the k times 15. Take out your little calculators, folks. This cancels, and you get 0.99957 equaling e to the 15k. And algebraically, let's solve for k. Take the ln of 0.99957 equaling over 15 equals k. What do you get? Okay. Negative 2.87 times 10 to the negative fifth. Okay, there's k. So how is my modeling? And notice what I'm doing is I'm modeling an actual phenomena. Do you think that plutonium that I have in my backyard actually cares if I'm doing this? Do you think it's decaying because I told it had to decay because I'm doing these numbers? It's amazing what math can do, folks. That stuff in my backyard is just decaying like it's going to decay. But because we found a natural principle, a property of that decay, we're able to mathematically model it and predict how long it's going to take for half of it to go bye-bye. Because now my decaying formula is going to be A equaling a sub naught e to the minus 2.87 times 10 to the negative 5 t. This is now a mathematical model that depicts the decaying properties of that plutonium. If I want to know my half-life, well, I need to plug in a certain time that'll give this to be half of this, right? So now I'm just going to solve for t. I'm going to say, plug in this condition to find my half-life. A will be 1/2 a sub naught equaling a sub naught e to the minus 2.87 times 10 to the minus 5 t half-life. So when the time is the half-life, I'm going to have only half of what I started with. This cancels with this. You get 1/2 equaling e to the minus 2.87 times 10 to the minus 5th, and it's just algebra now. Take the ln of both sides, you get the ln of 1/2 equaling a negative 2.87 times 10 to the minus 5 t to the 1/2. So what is your half-life? go. 24,150 years. Now, the way we categorize radioactive materials is really by their half-lives. All right, we study radioactive decay based on their half-lives. And because, folks, plutonium, whether it's in my backyard or in your backyard, will decay, half-lives never change. Half-life a million years ago for plutonium is the same as the half-life of plutonium today. Half-life is a constant in nature. This is how we can actually use half-lives of certain radioactive material to carbon date, for example, to date material. If for something, for example, you found a woolly mammoth. Now let's go even further than that. You found a brachiosaurus or velociraptor. Okay, 65, and actually velociraptors, I don't know if they were around 65 million years ago. You found something that was really freaky. Some sea monster. Oh, Loch Ness monster, you know, because he's been around for billions of years, right? At least the story has. And you wanted to, and this beast was frozen in ice. And you want to know how old this beast was. Something you found, you know, on your last summer trip to Montana. You know, playing around in somebody's backyard, you had a little bit of ice, chipped it away, all of a sudden a big beast was frozen. So what do? You take a little bit of its, make sure you don't wake it up, take a little bit of its skin, take a little bit of its carbon, find the carbon-14 that's in it, because that's the radioactive carbon, and by knowing, because it's radioactive material, knowing the properties of radioactive carbon-14, you can actually calculate how long that carbon-14 in that beast has been decaying, because you know the half-life. And from pretty much reverse mathematics, modeling it, reverse mathematics, you can find how long that thing's been around. Assuming that when it was alive, the amount of carbon, lock the door on us. Okay, we're here for the weekend. I can keep going. Oh, they just opened it, they heard me. That the amount of carbon in that beast when it was alive was the same amount of carbon that you would find in an elephant, and a human. And we find how much that baby has decreased over the years, and you know how old it is. 65 million